This is part 4 of the chapter 2 lecture notes, and honestly, I'm going to try to go through a little bit faster than I have been because we have 47 slides. So I was trying to go slow and explain everything, but with the functional groups, it's just a matter of recognizing them. If it's a carboxyl group, there's carboxyl groups in some of the organic acids, like citric acid that you find in fruits. So a carboxyl group is simply a carbon double bonded to an oxygen, single bonded to an OH. Sometimes it's written COOH. So sometimes you'll see it written like that, but the structural formula is shown here. An amino group is found in amino acids, and that's going to be a nitrogen bonded to 2 hydrogen atoms. Phosphate groups are characterized by the presence of phosphorus and oxygen, but it's a phosphorus double bonded to an oxygen, single bonded to an OH, single bonded to a second OH, and single bonded to another oxygen. So in other words, phosphorus forms 5 covalent bonds. It forms even more covalent bonds than carbon does. But for different reasons, it's not as useful as carbon in the building blocks of living things. But that's a phosphate group. A methyl group, just like methane with CH4, well, you call it a methyl group if one of the hydrogens is replaced by some chemical R. So a methyl group is CH3. It makes the chemical nonpolar, or at least that part of it is nonpolar. A carbonyl group means that you've got 2 chemicals on the end. You've got the R and the R, which can be anything. Any chemical or group of chemicals can be there. But in the middle between those 2 chemicals is a carbon double bonded to an oxygen. And the key here is that it be in the middle between 2 groups. So that's a carbonyl group. A sulfhydryl group is sulfur bonded to a hydrogen, sulfhydryl. An acid group, okay, so now we're on to a different thing. We're past the functional groups and we're moving on and talking about acids. I'm sure you know a little bit about acids. We know that acids typically taste sour and that they can be corrosive. But what it is chemically is something that releases hydrogen ions in solution. So one of the most common acids is hydrochloric acid, HCl. When hydrochloric acid dissolves in water, its hydrogen donates an electron to its chlorine. So they become hydrogen with a positive charge and chlorine with a negative charge, very similarly to how sodium chloride forms. And that is why we say that acids donate hydrogen ions, because when that hydrochloric acid dissolves in water, it splits up into hydrogen ions and chloride ions. So it increases the hydrogen ion concentration in the solution, and it lowers the pH. Anything that adds hydrogen ions to the solution lowers the pH and makes it more acidic. Bases, which we also use the word alkaline, not acidic, but alkaline, either they donate hydroxide ions or they remove hydrogen ions. They remove hydrogen ions. So I'm going to write it this way. They either donate hydroxide or they remove hydrogen. If an acid adds hydrogen, then a base is opposite, so it removes hydrogen. And a base will raise the pH. So when we talk about pH, neutral is 7. Anything above that is a base or alkaline, and anything below that is an acid or acidic. So any chemical that adds hydrogen ions is going to lower the pH. any chemical that removes hydrogen ions or adds hydroxide ions is going to raise the pH. Okay, now a chemical is called a buffer if it is able to like resist a change in pH. It's able to keep the pH within a narrow range. So buffers, if hydrogen is added so the pH lowers, the buffer can absorb excess hydrogen and the pH will raise back to what it normally was. Or the buffer can absorb excess hydroxide and lower the pH. So what buffers do, they're chemicals that keep the pH in a narrow range required for survival. It's one of the body's regulatory mechanisms. It's one example of homeostasis, of how homeostasis is I guess you say the mechanism for it is how homeostasis occurs. So the diagram below shows the body's buffering of blood pH levels. The blue arrow shows the process of raising the pH as more CO2 is made, and the purple arrow indicates the reverse process, the lowering of pH as more bicarbonate is created. So this is carbonic acid, and we'll start on the right instead of the left. So what happens is when we breathe in carbon dioxide, some of that carbon dioxide is used to make, I'm sorry, I was about to say something stupid. I'm sorry. When we breathe in carbon dioxide, it goes through the process called cellular respiration a lot of times. But some of the carbon dioxide just combines with water and forms carbonic acid. And then that carbonic acid breaks up in solution and releases this bicarbonate ion. And sodium bicarbonate is baking soda. And you may realize that baking soda is a base. So by adding bicarbonate ions to the solution, it raises the pH. I'm sorry. Okay, honestly, I was thinking about re-recording that 7 minutes just so I could delete this error that I just made because I just told you something opposite of what it's supposed to be and I caught myself. But I'm not going to delete it. Everybody makes mistakes. I hope you'll forgive me. But I don't want to go back and redo that 7 minutes. So let me be clear. Okay, so this is carbonic acid. But what happens in the body when carbon dioxide combines with water, it forms carbonic acid. And when that carbonic acid splits up, it splits up into hydrogen ions and bicarbonate ions. Now, bicarbonate ions by themselves could raise the pH, but because this is splitting up and releasing hydrogen ions, when the reverse reaction, meaning going from the right to the left, when that reaction occurs, the pH is lowered. It lowers the pH. It makes the blood or the body fluids more acidic. But in the reverse process, if the body fluids are already more acidic and they need to be raised, so you won't go into what's called acidosis, then the hydrogen ions combine with the bicarbonate ions, the HCO3 minus is bicarbonate, form carbonic acid, and then the carbonic acid breaks up into carbon dioxide and water, and eventually the carbon dioxide reaches our lungs and we breathe it out. So as we remove carbon dioxide, the pH is raised. And it's also the very beginning of the reaction is by forming carbonic acid, hydrogen ions are being removed from the solution, and that's always going to raise the pH. So that's a buffer. It's just a system of chemicals that can absorb, either add hydrogen ions or remove hydrogen ions from solution in order to keep the pH at a normal range. Okay? All right, so chemical reactions. We're just going to do some basics. Chemical reactions occur when two or more atoms bond to form molecules, or when bonded atoms are broken apart, or sometimes when atoms just change places. We call that an exchange reaction, or displacement. But anyway, the reactants before the chemicals before the arrow are called the reactants. They're like the ingredients in a recipe. They're what you start with. And the products, which are on the right side typically, water is the product in this reaction. The products are what is formed, what is produced. Now, if you go back to this reaction, it just depends on which way the reaction went. If the reaction proceeds to the right, then the reactants are hydrogen and bicarbonate, and the products eventually are water and carbon dioxide. But then if it goes the other way, the reactants are water and carbon dioxide, and the products are hydrogen and bicarbonate. So it depends on which way the arrow is. Whatever the arrow is pointing at, that's a better way to say it. If whatever the arrow is pointing at is the product, okay? So this is an example of a compound that you probably recognize, water, and it shows you how the electrons are shared, so I'm glad for that. Hydrogen has one electron, period. It doesn't just have one valence electron, it only has one electron. It's got an atomic number of 1, meaning it has one proton, so it only has one electron. So it needs 2 in its first energy level in order to be stable. So what happens is hydrogen shares an electron with oxygen. Now hydrogen has 2. Each hydrogen has 2. And since each hydrogen provided one electron to the oxygen by sharing, then the oxygen now has its 8. So that this is an example of a compound that forms by covalent bonding. And then there's a section here on balancing chemical equations, meaning that the number of atoms on the reactant side need to be equal to the number of atoms on the product side. So, gosh, okay, so let's just go back to I'm just going to do part of that carbonic acid reaction. So this is carbonic acid, and it reacts to form carbon dioxide plus water. So it's already balanced. It doesn't have to have any numbers or coefficients in front. But the way you know is that what I do is I just start hydrogen, carbon, and oxygen are the atoms that are in this chemical equation. So on the left of the equation, there are 2 hydrogen atoms. That H2 means there's 2 hydrogen atoms. And on the right, there are also 2. So hydrogen is balanced. On the left, there's 1 carbon atom, and on the right, there's 1. That 2 in front of the oxygen is for oxygen, not carbon. And then on the left, there are 3 oxygen atoms. And then if you add up 2 here and 1 here, you've got 3 oxygen atoms on the right. So if this weren't balanced, we would have to put numbers or coefficients here, here, and possibly here in order to balance the number of atoms. All right, an irreversible reaction can proceed only in one direction until all the reactants are used up. So it only proceeds in one direction. A reversible reaction can go in either direction. The carbonic acid reaction, that is a reversible reaction. It goes in either direction depending on the conditions. So sometimes equilibrium is reached and the reaction occurs equally in the forward and the reverse direction. So products are formed just as fast as on each side of the equation. Like if this were an equilibrium, the water and carbon dioxide would be produced just as fast as hydrogen and bicarbonate, hydrogen ion and bicarbonate. All right, so it's anabolic if it is a building reaction, if it's a synthesis reaction. It's catabolic if it's a breakdown reaction. Every time we break down molecules in the food that we eat, it's a catabolic reaction. Catabolic reactions release energy. Anabolic reactions require energy.